Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis, so according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power, or degree, of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension. So why is this extra dimension that numbers possess not common knowledge? Part of the reason is that it has been given a terrible, terrible name. A name that suggests that these numbers aren't even real. In fact, Gauss himself had something to say about this naming convention. So yes, our missing dimension is comprised of numbers that have been given the ridiculous name imaginary. Gauss proposed these numbers should instead be given the name lateral, so from here on, let's let lateral mean imaginary. To get a better handle on imaginary, I mean lateral numbers, and really understand what's going on here, let's spend a little more time thinking about numbers themselves. Early humans really only had use for the natural numbers, that is 1, 2, 3, and so on. This makes sense because of how numbers were used. So to early humans, the number line would have just been a series of dots. As civilizations advanced, people needed answers to more sophisticated math questions, like when to plant seeds, how to divide land, and how to keep track of financial transactions. The natural numbers just weren't cutting it anymore, so the Egyptians innovated and developed a new high-tech solution: fractions. Fractions filled the gaps in our number line and were basically cutting-edge technology for a couple thousand years. The next big innovations to hit the number line were the numbers 0 and negative numbers, but it took some time to get everyone on board. Since it's not obvious what these numbers mean or how they fit into the real world, 0 and negative numbers were met with skepticism and largely avoided or ignored. Some cultures were more suspicious than others, depending largely on how people viewed the connection between mathematics and reality. And this is not all ancient history. Just a few centuries ago, mathematicians would intentionally move terms around to avoid having negatives show up in their equations. Suspicion of 0 and negative numbers did eventually fade, partially because negatives are useful for expressing concepts like debt, but mostly just because negatives kept sneaking into mathematics. It turns out there's a whole lot of math you just can't do if you don't allow negative numbers to play. Without negatives, simple algebra problems like x plus 3 equals 2 have no answer. Before negatives were accepted, this problem would have had no solution, just like we thought our original problem had no solution. The thing is, it's not crazy or weird to think these problems have no solutions. In words, this algebra problem basically says, if I have 2 things and I take away 3, how many things do I have left? It's not surprising that most people who have lived on our planet would be suspicious of questions like this. These problems don't make much sense. Even the brilliant mathematicians of the 18th century, such as Euler, didn't really know what to do with negatives. He at one point wrote that negatives were greater than infinity. So it's fair to say that negative and imaginary numbers raise lots of very good, very valid questions. Like, why do we require students to understand and work with numbers that eluded the greatest mathematical minds for thousands of years? Why did we even come to accept negative and imaginary numbers in the first place when they don't really seem to be connected to anything in the real world? And how do these extra numbers help us explain the missing solutions to our problem? Next time we'll begin to address these questions by going way back to the discovery of imaginary numbers.
I've got the tutorial question 3A and question 9 on the textbook. Was there something else? Sarah, did you say there was another one? Another question?
Yeah, there's someone's asking for question 5 as well off the tutorial.
Off the tutorial. Please. Okay, so I'm going to do the textbook first, and then I'll do the tutorial. So on the textbook, it was question 9. Right, which is pirates, good old pirates. So let me just put that on the screen so you've got the question. So it's question 9. The pirate boat is 20 kilometers away from you on a bearing of 135 degrees. It's travelling at 20 kilometers an hour. Hang on, it is travelling at 20 kilometers an hour on a bearing of 45. You can travel twice that speed. What bearing do you need to set to catch the pirates in the shortest possible time? Okay, let me move that over there and let's do a diagram of what's going on here. So a pirate is 20 kilometers away from you on a bearing of 135 degrees. Right, just so you know, bearings are always measured, there's north, they're measured clockwise from north. So that's how you measure bearings. So they start at 0, obviously that's due north. At 90 you're going due east, at 180 you're going due south, at 270 you're going due west, and then when you get back to here, 359 is almost north, and then you take one more degree and you're back to 0. So it's a modular system. So you don't get angles, you don't get bearings that are greater than 360 degrees. 361 degrees would just become 1 degree. Right, so pirate boat is 20 kilometers away from you on a bearing of 135. So that's you. 135 is going to be down there, isn't it? Okay, so this is the pirate boat. Okay, and that is 20k, 20 kilometers, and the bearing there is 135 degrees. Okay, it is traveling at a bearing of 45 degrees, so let's change my pen color. It's actually doing it like that. That angle there is 45 degrees. Okay, it's traveling at 20 kilometers an hour at a bearing of 45 degrees, so that's 20 kilometers per hour. Okay, your boat can do twice that speed, so what bearing do you need to set? So I've done that a little bit too long. Let me just shorten that a little bit. So if I bring that in a bit, back to there, that's what it's doing. So what you need to do, and I'll put you in green, is you want to do some kind of angle to catch them there. Okay, and you need to find out what this angle here is. Okay, so before I dive into this, can I give you 5 minutes to have a go at it, to try to work out what you know about the question there? And your speed there is 40 kilometers per hour. So we have got a triangle here, which is obviously where we need to start. Can we work out what this angle is here? If I take that straight up like that, and this one across here like that, so that's a right angle that I've got in there. This angle here we know from the horizontal, so from the horizontal is 45 degrees, don't we? We know that because this whole bearing is 135 degrees. We also know that this is 45 because we've measured that bearing, which means that this angle here is 45 and this angle here is 45, which means that this triangle, the speed triangle, is a right angle triangle. 40 is the hypotenuse and 20 is the base of the triangle, if you see what I mean. Which means that I can calculate this angle here, can't I? And this time it's right, let me just go through this quickly, because again, people see these in different ways. But imagine this is the top of your head, that's your shoulder, and these are your feet. Okay, so that's you sitting there, and there's your hair. So I'm looking straight down on somebody's head, right? And I'm looking along that line. So I've got a triangle here. This is central, and this is sideways. Okay, so central is cos, and sideways is sine. So that's how I visualize what angle I'm looking at. Now, we've just shown that this angle down here is a right angle, which means that if I imagine myself standing here, head, shoulders, and feet, and I'm wearing black shoes, okay, this is the central direction, and this is the sideways direction. Do you see what I'm saying? The black line over the green line will be the cosine, but I don't know the black line, but I do know the blue line, and that's the sideways one. So what I can say is, if I call this theta here, that's the, let me do it in green, Z, 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 because that's the angle I'm looking for, theta there. Sine theta is equal to 20 over 40. Okay, so obviously sine theta is equal to a half, which actually tells you what the angle is. I'll just show you that because that's worth knowing. Here's a couple of triangles. This is yet another aside. Excuse me giving you all these asides. Come on, mouse, where are you? So let's move that up there. Right, let's take this triangle, which is, that's an equilateral triangle, so that side is 2, that side is 2, and that side is 2. So these angles are all 60, aren't they? So if I drop a perpendicular down there, this angle is 30. So that is 2, and I've split that, so that side is 1 and that side is 1. So this side here is 2 squared minus 1 squared, so that side there is root 3. So that means I can say that sine of 30 equals, that side there is 1, that side there is 2, is 1 over 2. Okay, I can also say that sine of 60 is equal to, because I'm now down in this corner, and it's going to be root 3 over 2. And I can also say that cos of 30, so let's do that, cos 30 is equal to cos of 30, so that's root 3 over 2. Cos of 60 is equal to, so here's 60, it's 1 over 2. And obviously I can do tan of 30 or 60 in exactly the same way. So that is one standard triangle that you can calculate these things without even having a calculator. So what I'm going to do there is say that, just remind ourselves, sine 30 is a half, so sine 30 is a half, so that means I can say here that theta is equal to 30 degrees. Okay, so if I drag that down again, what I'm saying then is that this angle in here, I'm going to colour it in because that diagram's got a bit scruffy now. So this angle in here, that green angle there, is 30 degrees. So the bearing is going to be, so 30 degrees there, this is 45 to the line, so the little bit in there is 45 minus 30 is going to be 15, and obviously we've got 90 going on there, so 90 plus 15 is 105 degrees, so the bearing is equal to 105 degrees. Okay, so what bearing do you need to set to catch the pirates? And that's all it's asking. Is that okay? Is that clear enough? Because that's the sort of question you're likely to find on your exam paper. Do we understand that? Do you want me to go over it again? can I zoom out? Do you mean do this sort of thing? So you've got, yeah, okay. And so I'll go over it again, and this time I won't do all this side stuff that we've done. Yeah, okay, I'll do that then. So let me go back in again. Oh, you got what you needed, whoever wanted me to zoom out. Zishan. Yep, okay, so I'm going to clear the page. Come on, clear my canvas. And go back in again to 100%. There we go. Right, so what we've got is here's U. I'm going to try to draw this much tidier than I did before. Oops, let's have a pen. So here's U, and the pirates are down here at a bearing. So a bearing of 135, sorry. So there's north in that direction. So I come round 90, which takes it to east, and then that means I need another 45 degrees. So it's going to be down there. Okay, so this whole bearing is 135 degrees. Okay, and let's just draw the horizontal line in, because that's quite handy. Right, so now the pirate boat, which is 20 kilometers away, okay, on the bearing of 135 degrees, it's traveling at 20 kilometers an hour, and it's at an angle of 45, at a bearing, sorry, of 45. So if I draw a vertical in there, I need a bearing of 45, which is going to go up like that. So that's 20 km per hour, hour, there we are. And this is 45 degrees. And what we need to do is to calculate what bearing we need to set to catch them. Okay, so this angle here, from the horizontal to the diagonal line there, is 45 degrees, because that's 90 minus 135. So if I were to draw that line to the top there, I've got 45 degrees. Remember, it's to this line here. So if I were to draw that in, I know that this is 45 degrees, which means that I know that that is a right angle, and that's really important. So they're going at 20 kilometers an hour. You have got a fancy boat. You're going at 40 kilometers per hour. Okay, so now just looking, let's take that triangle out of here. So we've got a triangle now that looks like this. We don't know this distance, but we do know that this is 20 km per hour, and we know this is 40 km per hour. And what I'm saying is that if I were to stand here and look down there, that's central, and this is sideways. So the angle here, theta, so is I need the sine of theta. So sine theta is equal to 20, which is this distance, divided by the hypotenuse, which is 40. Okay, and that's equal to a half. So theta is equal to, what did I say, 30 degrees, didn't I? So 30 degrees. Are we okay with that? Everybody happy where that came from? Yes, I am recording this as well. So what we've said then is that the angle that I'm going to mark in red, no, blue, because that's what that line is. So the angle in blue there is 30 degrees, excuse me, 30 degrees. Okay, now let's just think about this line here, so that we've got 90 to the horizontal, and then an additional 45 back to the horizontal, and we're only going back 30, which means that this little bit in here, let's change colour again, this little bit in here is equal to 45 minus 30. So that is equal to 15 degrees. So the bearing, I'll do that in red, so the bearing is equal to 90 plus 15 degrees is equal to 105 degrees. Okay? Yep. How can you use speeds as distances? Great question, Alexander. What I'm doing is, because they're both in the same units, kilometers per hour, and yeah, they're both kilometers per hour, I'm using effectively similar triangles. Because it's not asked me, the question doesn't say how long is it going to take you, because then I would need to use the distance. But for the moment, if this whole thing took an hour, then sorry, I'm pointing with my finger, which you can't see. If this whole thing took an hour, let's say, this distance would be 40 kilometers and this distance would be 20 kilometers. But for now, I'm just using similar triangles. So the ratio of this side to this side, if it got bigger or smaller, the ratio would stay the same, which means that the angle would stay the same. So great question, really good to think that through, but it's similar triangles is what I'm using. Is that okay? But you definitely can't mix kilometers and kilometers per hour. You definitely can't do that. Would you have to meet the pirates at the same time? So the time would be... Yeah, the point, Mohammed, is that these are simultaneous equations, which means that in this particular case, the pirates didn't see you coming, so come on, mouse, where are you? The point here is both boats arrive at the same place at the same time, which means that people then start shooting guns and all that sort of stuff, like pirates always do. So yes, you both get to the same point at the same time. And just for the record, these are straight lines, aren't they? And the shortest distance between 2 points is a straight line. So if the question said, what is the minimum time required, you would use exactly what we've done here. Okay? Right, so let's move that up and see if I can't copy in a question. Control V. Yes, it works. So let's move you to there. Right, can I give you a couple of minutes to think that through? So a lion spots a zebra. So lion sees the zebra. Okay, I hope you don't mind my rather scruffy diagrams, and the distance between them is 200 meters. Okay, let's imagine they both set off in that direction, because the zebra is going to run away from the lion, not towards it, obviously. The zebra is going at 64 kilometers an hour, and the lion can go at 80 kilometers per hour. Okay, so how long will it take the lion to catch the zebra, assuming they both start at the same time? Right, so what we're going to do is we're going to have two equations. We're going to have the time. So let's imagine that the time is what we're going to calculate to these two intersecting, is effectively what we're talking about. Now, let's imagine there's a distance x here before death. Okay, so the distance that the lion will run is going to be 200 plus x, so that's the distance over speed is equal to time, and the distance the zebra will run is just going to be x divided by, which is equal to the same time. Why is it the same time? Because they meet at that point there, don't they? Is that okay? So distance over speed equals time. That's distance, that's speed, and that's equal to time. It's a bigger distance for the lion, but it's a different speed for the lion, and that is equal to the same time, because that's the time when the poor old zebra gets converted into dinner. Okay? Yeah, I will go further than this. So what we're going to do is I'm going to cross multiply these two equations, because we've got a section B there, haven't we? So we're going to get 200 plus x times 64 is equal to 80x. Okay, so what I'm going to get then is I'm I'm going to get the x's on the left hand side. No, I'm not. I'm going to get the x's on the right hand side. So I'm going to have 200 times 64 is equal to 80 minus 64 brackets x. Okay, see what I did there? So 80 minus 64 is going to be 16. So 16x is equal to 200 times 64. So x is going to equal, bear with me, I'm going to divide the 200 by 2, so that's going to be 100. I'm going to divide the 64 by 8, so that's going to be 8. So x is equal to 800 meters. Just so you see what I was doing there, I can divide 64 by 8 easily, because 8 squared is 64, and then I'm left with 2, but I've got 200, so I may as well divide that. So there we go. X is equal to 800 meters. And what I want to do, if I'm being sensible, is I'm going to say 200 plus 800 is 1000 over 80 is equal to x is 800 over 64. So that's going to be 100 over 8, which is equal to 25 over 2. And then 800 over 64 is equal to 8 into both of those, which is 100 over 8, which is actually the same as that, isn't it? Okay, so that's another yippee moment, because we got that right. Okay, so we now know the distance that each of them goes, and the second part of the question is, what distance will the lion have travelled to catch the zebra? Well, 200 meters plus 800 meters, it's going to have run a kilometre. So that's going to be 1 km. Why don't I do straight into here? So I'm going to make that bigger because I need a bit of space. So intersection between, and then I'm going to copy those like so. Control C, Control V. Okay, and then I need to fix those so it's 2x plus 21 and 3x is equal to 4x squared plus 8x plus 3. So then what I want to do is to copy those, Control C, Control V. So this one I'm going to call equation 1, and this one I'm going to call equation 2. Right, so my answers have been updated. So I can write equation 1 like that and equation 2 both equal 3y. So now I can say, so can I just paste? Yes, I can. So now I can say that 2x plus 21, that's right, is equal to 4x squared plus 8x. Right, so now I'm going to move everything onto the left hand side, and I'll change the signs whilst I'm doing it, so just be careful here and make sure you know what I'm doing. So I'm doing 4x squared plus 8x plus 3 minus 2x minus 21 is equal to 0. Okay, which means that 4x squared plus 6x minus 18 equals 0. And then you've just got a quadratic to solve. And then what you're going to get is give the point with the smaller x value. So you're going to do some arithmetic, and then down here you're going to end up with answer, and then it's going to be an x value, which is the smaller x value, and a y value. And then in the next one, what would I write here? I'd say from above. Then I'd say answer will be an x value and a y value. So that's how you would answer a question like that, because sorry, I keep pointing with my finger, which you can't see. So in this one, you'll get two values. There'll be a smaller x value. I would do sanity checks and things on like that to make sure I've got it. You can obviously check it to make sure it's okay. If it's blue, then it's text. If it's black, it's arithmetic, and the answer will be in green. So that's okay, and that's how you would put your answer in. Okay, so let's just make that a bit smaller. Does that sort of cover the question, Mohammed? Are you okay with that? Right, so it says larger x value, so I put it both x and y. Right. Yeah, it says here, give your answer in the form of brackets x, comma y. So you do need brackets, the x value, comma, the y value, and give your number up to 2 decimal places, which means that if the answer is 4, put 4. If the answer is 4.1 or 4.2, put 4.1 or 4.2. If the answer is 4.1, 2, 3, 4, 5, 6, 7, 8, 9, just put 4.12. That's what that means. But it says give your number in the form of a Cartesian coordinate, which is what that is, okay? But with the smaller x value in this one and the larger x value in that one. Is that okay? Okay, any other questions? If the answer is 4.356, then do you round it? Yes, you definitely do. And if you don't, you'll be marked wrong. So it's 4.36 will be the answer to that one. Yes, 4.36. That's what you need to put in. Any other questions? And I will put up a video of this